Okay, so let's unpack this.
Yeah.
We all do it. You get in the car, the sun goes down, you twist a knob, or if you're in a newer car, you just let the sensors do their thing and boom, light.
Right. It feels completely automatic.
Yeah, it just feels like a basic, boring part of the car.
It does feel basic, yes.
Yeah.
But it is arguably the single most critical safety device on the vehicle, mostly because of how incredibly dangerous the alternative is.
And that is exactly where I want to start our deep dive today. Because I was reading through the research for this, and I found a statistic from the National Highway Traffic Safety Administration that honestly floored me. I had to read it twice.
Oh, I think I know the one you mean.
Yeah.
The fatality split.
Exactly. So nearly half of all traffic-related fatalities happen in the dark. But here is the kicker context for you. Only about 25% of all travel actually happens during those hours.
Right.
So you're driving way less, there are way fewer cars on the road, but the risk of dying is exponentially higher.
The risk density is just off the charts. And standing between you and that statistic is the entire subject of our deep dive today. We're looking at the history, the physics, and the really surprisingly dramatic politics of the automotive headlamp.
And actually, before we go any further, I should probably correct myself right now, shouldn't I? Because I keep wanting to say headlight.
Oh, it's the most common mix-up in the industry.
Yeah.
But if we want to be precise, and for this deep dive we definitely do, the headlamp is the actual physical device, the hardware installed in the front of the car.
Right.
The headlight is the beam of light that actually comes out of it.
Okay, so headlamp is the hardware, headlight is the beam. I will try to keep that straight.
It takes practice.
So today we're going on a pretty wild journey. We're going to go from literally carrying fire in a box on the front of a carriage,
Which was exactly as dangerous and ineffective as it sounds.
to the frozen era, where American law basically banned innovation for decades, to the nostalgia of pop-up lights, and finally to lasers and matrices that can essentially see around corners.
It's a massive trajectory. We've gone from burning gas to digitally controlled pixels in just over a century.
So let's rewind, way back, before the Model T even. If you were driving a horseless carriage in, say, the 1890s at night, what were you actually using?
Well, you're using legacy technology. You're using carriage lamps, which were designed for, well, carriages pulled by horses.
Makes sense.
And horses, generally speaking, don't move very fast, and they have their own eyes. So these lamps usually just burn candles.
Candles, like literal wax candles.
Literal wax candles inside a little glass box, which, as you can imagine, are terrible for speed. If you're doing 20 miles an hour in a vibrating metal contraption, a candle is not going to show you a pothole until you are already in it.
And I imagine the wind is an issue.
Constantly blowing them out. So you obviously needed something brighter and tougher. Enter the acetylene era.
Okay.
This runs from the late 1880s into the early 1900s. Acetylene is a combustible gas. It burns with an incredibly bright white flame, and crucially, the flame is highly resistant to wind and rain.
So how did you get the gas into the lamp? Did you have a tank in the car?
Sometimes, yeah. There was a system called Presto O-Light, which was very popular. You'd have this calcium carbide gas generator strapped to the running board of the car.
Okay.
It would feed gas through these little copper pipes up to the lamps. But here's the sensory detail that we totally forget today, the ritual of it.
Right, because you couldn't just flip a switch inside the cabin.
No way.
Yeah.
You had to physically stop the car, get out, walk to the front, open the glass lens, turn on the gas valve, strike a match, and hope the wind didn't blow it out or that you didn't put your fingers.
Wow.
Then you had to walk around and do the other side. It was a very physical interaction with the machine.
I can definitely see why people wanted electricity pretty badly at that point. But electric lights existed in homes by then, so why not cars?
Oh, they tried.
Yeah.
The Columbia electric car had optional electric headlamps in 1898.
Oh, wow. Early.
But there were two massive engineering hurdles. First, the dynamos, the generators needed to power them, were massive and heavy. But the bigger problem was the filament itself.
They were too fragile.
Yeah. Carbon filaments in 1898 were delicate things. And the roads back then were incredibly rough. Cobblestones, dirt ruts.
Right. No smooth asphalt.
Exactly. The vibration would just shake those delicate filaments until they snapped. You'd hit one bad bump, and suddenly you were in total darkness.
So it just wasn't practical at all.
Not until 1912. That is the real pivot point.
Yeah.
Cadillac integrated the Delco electrical ignition and lighting system. It was the first modern electrical system. Suddenly you didn't need a match. You just needed a switch.
And that leads to the next big leap in the 20s, right? The Billups bulb.
Right, in 1924. Before this, if you wanted a high beam and a low beam, you often had complex mechanical dippers or entirely separate lights.
Which sounds expensive.
Very. The Bilex bulb put two filaments in one single bulb, one for the main beam, one for the dipped beam. It is the grandfather of the standard bulb we use for almost a century.
Okay, so we have electric lights, we have high and low beams, we were making serious progress. But then we hit what I like to call the Great Stagnation, specifically in the US.
This is such a fascinating piece of regulatory history that really shaped the visual identity of American cars for decades.
Because in 1940, the US government handed down a mandate.
Yes. Every vehicle, no matter the size, the shape, the brand, or the price, had to use two 7-inch round sealed beam headlamps.
And sealed beam meaning the lens, the reflector, and the filament are all one permanently fused unit.
Correct. If the bulb burned out, you didn't just change a little bulb. You threw the entire glass unit away and bought a new one.
What was the logic behind that? It seems incredibly wasteful.
It was actually sound engineering at the time.
Mhm.
Headlights back then had a major problem where moisture and dust would leak in behind the lens.
Oh, and ruin the mirror?
Exactly. The silver reflector would tarnish and get dull. So the light got dimmer and dimmer over time without the driver really noticing, which was super dangerous. Sealing the whole thing prevented that entirely.
Okay, so good for durability, but bad for design.
Terrible for design. Imagine being a car designer in the 50s. You want to make a sleek, futuristic car, maybe a low shark nose.
Right.
Too bad. You have to slap two giant 7-inch glass circles on the front, upright and exposed. It completely froze lighting technology in the U.S. until the 70s.
Though they did tweak it a little in 1957, right?
They did. They allowed 4 slightly smaller round lamps, the classic quad headlights you see on late 50s and 60s muscle cars. But still, round sealed beams only.
And meanwhile, Europe is just doing its own thing.
Europe never mandated sealed beams. They stuck with replaceable bulbs behind different shaped lenses. So by 1960, you see cars like the Ford Taunus or the Citroen ami6 with rectangular lamps or oval lamps.
Which was completely illegal in America.
Totally illegal.
And then comes the halogen breakthrough.
Huge moment. 1962, Europe introduces the H1 halogen lamp. It uses a tungsten filament, but it's encased with halogen gas, which creates this clever chemical cycle that redeposits tungsten back onto the filament.
So it heals itself.
Essentially, yes. Result being it burns brighter, hotter, and lasts way longer.
And let me guess. The US government said no thanks.
Essentially, yes. Halogens were effectively banned in the U.S. because regulations had a strict cap on how bright lights could be. They basically looked at it and said, that works too well.
That is wild.
It wasn't until 1979, almost 20 years later, that halogen-sealed beams were finally allowed in the States.
2 decades of driving with dimmer lights just because of a regulation. But speaking of different regulations, we have to talk about France. Because if you watch old movies or look at vintage photos from Europe, French cars always had these bright yellow headlights.
Ah, the selective yellow. This is a great story. From 1936 all the way to 1993, France required headlamps to emit yellow light, not white.
Why? Was it just a style choice?
Ostensibly, it was safety. The French Academy of Sciences claimed that yellow light reduced glare and was better in fog because the longer wavelength scattered less than blue or white light.
Okay.
They argued it reduced driver fatigue.
But is that actually true?
The science is mixed at best. UK research in the 60s showed maybe a 3% improvement in visual acuity. But later, Dutch research said there was basically zero difference.
So if the science was that shaky, why keep it for 60 years?
Well, there's another theory. Protectionism.
Keeping the foreign cars out.
Look at the start date. 1936. Tensions in Europe are very high. During World War II, the yellow lights distinguished French civilian vehicles from military ones.
Right.
But after the war, it acted as a very effective trade barrier. If you were a German or American automaker and you wanted to sell your cars in France, you had to manufacture a special separate set of yellow lamps just for that one market.
Which is a massive hassle.
Exactly. It gave a slight but real edge to domestic French manufacturers.
It's amazing how much geopolitics is involved in a light bulb.
Always. Technology never exists in a vacuum.
Okay, let's move to something a bit more fun. Design. Because even though the US had these strict shape laws, designers were actively trying to fight back. And that battle gave us one of the coolest features in automotive history, the pop-up headlight.
The hidden headlamp. This is a classic case of engineers solving a regulatory problem with mechanical complexity.
How so?
Well, designers wanted low, sleek aerodynamic hoods. But the U.S. law said the headlamps had to be at a certain specific height, usually about 2 feet off the ground, and they had to be uncovered circles.
So if you can't change the light, you just hide it.
Exactly. You make the hood sleek during the day
Yeah.
and then mechanically raise the lights to the legal height at night. The first one was actually way back on the Cord 810 in 1936.
And those were completely manual too, right?
They were. You had a little hand crank on the dashboard.
Hmm.
You literally had to wind them up like a window.
That is true dedication to style. Just hold on a second. Let me crank up my headlights.
But the true golden era was the 60s and 70s. The Corvette, the Ferrari Daytona, the Lamborghini Countach. It allowed the car to look like a wedge cutting through the air.
So cool.
Then at night, vacuum-operated servos or electric motors would kick in and pop. Up come the lights.
But there was a real victim of the U.S. regulations in this era, too. The Jaguar E-Type.
Oh, an absolute tragedy for car lovers. The original E-Type is widely considered one of the most beautiful cars ever made.
Right up there.
It had these lovely sculpted glass covers over the headlights to make them perfectly aerodynamic, following the exact curve of the fender. Then in 1968, the U.S. passed FMVSS 108, which explicitly banned covered lights.
Why ban the glass cover?
They were worried about the glass reducing the light output or getting dirty and reflecting glare, so Jaguar had to remove the glass and just leave these naked scoops in the hood.
Which ruined the lines.
Completely wrecked the drag coefficient and the whole look of the front end.
So what finally killed the pop-up? Because you just do not see them anymore. Was it aerodynamics?
No, it was safety again. But this time, pedestrian safety?
Pedestrians. How
Yeah.
do headlights hurt pedestrians?
Think about the physics of an impact. You have a sleek car, but then you have these two rigid, sharp metal boxes sticking up straight from the hood.
Oh, I see.
If you hit a pedestrian, those pop-ups act like rigid protuberances. They cause severe injuries. So global regulations changed to limit sharp angles on hoods, and by 2004, the pop-up was effectively dead.
RIP to the pop-up. Now, I want to get into the physics of this a little bit, because we talk casually about high beams and low beams, but there is actually a really complex geometry happening in that beam pattern.
There really is. It is not just dim and bright. It is entirely about aim. A high beam is center-weighted. It throws light as straight and as far down the road as physically possible.
Because it doesn't care about blinding anyone, since you only use it when you're alone.
Precisely.
Huh.
But low beams have to play nice with others. Low beams have what we call a cutoff. If you shine your car lights against a brick wall, you will see a sharp horizontal line where the light just stops.
Right. But it's not a perfectly straight horizontal line across.
No, it is asymmetrical. In the U.S. and Europe, where we drive on the right side of the road, the beam dips low on the left to avoid blinding oncoming drivers.
But then it steps up on the right.
Exactly. It kicks up on the right side to illuminate road signs and pedestrians walking on the shoulder.
And this creates a very specific issue for travelers. I saw a term in the sources called the traveler's problem.
Oh, yes. This is a classic headache for anyone driving across borders with different traffic signs. Say you take a British car, which is obviously designed for driving on the left.
And you take it on a ferry into France.
Right, where they drive on the right.
Yeah.
Your kick-up is now on the wrong side.
Oh, no.
Your lights are dipping to the left, which is now the shoulder, and they are kicking up to the right, directly into the eyes of every oncoming French driver. You're blinding everyone.
So how do you fix that if you're just on vacation?
Historically, you had to buy these little opaque decals or stickers at the ferry terminal and physically stick them onto your headlamp lens to block that specific part of the beam. It's a legal requirement.
That seems incredibly low-tech for driving a modern machine.
It is, though. A lot of modern cars have a software setting in the dashboard now that adjusts the matrix. But speaking of beam patterns, there is a massive philosophical debate in the lighting world between the U.S. system, which is SAE, and the rest of the world, which uses ECE.
What's the core difference? Isn't light just light?
You would think, but the safety philosophy is fundamentally different. The ECE, the European standard, prioritizes preventing glare at all costs. They require a remarkably sharp cutoff.
So below the line is bright, above the line is dark.
Almost total darkness above the line, yes.
And the U.S.
The SAE standard actively allows for more scatter light above that horizontal line.
Why would they want scatter?
The argument is that America has vast, dark highways, and you need some ambient light thrown upwards to read large overhead highway signs that aren't internally illuminated.
But that upward scatter directly equals glare for the oncoming driver.
Exactly. It is a deliberate trade-off. The U.S. accepts a bit more glare to ensure you can read the exit sign from further away.
Yeah.
Europe says no, keep the light rigidly on the road.
Is one actually better?
Studies show neither system is definitively safer. It mostly comes down to what drivers in that region are culturally used to.
Well, speaking of glare, let's talk about the blue lights, the ones that absolutely everyone complains about on the highway.
The HID wars, high-intensity discharge, also commonly known as xenon.
Who's first showed up in the 90s, right?
Yes, first on the BMW 7 Series. Technically, they are arc lamps. There is no traditional filament at all.
So how does it glow?
It's a spark of electricity jumping between two tungsten electrodes inside a tiny quartz capsule filled with xenon gas and metal salts. It is quite literally a controlled lightning bolt in a bottle.
And they are incredibly bright.
Very. To put it in perspective, a standard halogen puts out maybe 1,400 lumens. An early HID puts out 3,000.
More than double.
But the real issue is the color temperature. They produce a very crisp white-blue light.
And that's what makes people so angry when they drive past them.
Yes, because human eyes react differently to blue light. It appears far more piercing to us. Studies have shown that even at the exact same measured intensity, an HID light is perceived as 40% more glaring to other drivers than the warm yellowish halogen light.
But the driver sitting behind the wheel loves it.
Oh, the driver feels invincible. You feel like you have high-definition night vision. It's a classic conflict of the driver's experience versus the oncoming traffic's experience.
And then came LEDs. The Audi R8 brought those to the mass market around 2007.
Light-emitting diodes, yes. They are hyper-efficient, they're physically tiny, and they allow for crazy design signatures because you don't need a massive round reflector. But they introduced a really funny new engineering problem, the cold lens.
The cold lens, what does that mean?
Think about the older lights. Halogens and HIDs generate a massive amount of waste heat. So if you are driving in a snowstorm, the heat from the bulb naturally melts the snow right off the front lens.
Oh, they self-clean. I never even thought about that.
Exactly. But LEDs are so efficient, they don't emit infrared heat forward. So you could be driving an ultra-modern car in a blizzard, and your headlights just get completely caked in snow and ice because they aren't hot enough to melt it off.
So you're just driving blind. What was the fix?
They literally had to engineer tiny internal fans or specialized heating elements into the housing just to blow warm air onto the plastic to thaw it.
It's a perfect case of new tech solving one problem energy use, but instantly creating a completely new one.
Welcome to automotive engineering.
We've also got lasers now, which honestly just sounds like science fiction.
It does. Cars like the BMW i8 and the Audi R8 LMX use them. But don't worry, they aren't shooting a raw laser beam into your retina.
Good to know. How does it actually work then?
Tiny mirrors direct a blue laser onto a special yellow phosphorus lens. When the laser hits the phosphorus, it gets excited and emits a brilliant, pure white light.
So the laser is just the power source for the glowing phosphorus.
Exactly. And it is incredibly energy dense. Half the power draw of LEDs. The Rolls-Royce Phantom 8 uses lasers to cast a high beam 600 meters down the road.
600 meters. That is more than half a kilometer of pure visibility.
It's staggering range. But range isn't everything anymore. We are now firmly entering the era of smart lights.
Which brings us to adaptive front lighting systems, or AFS. Now, this isn't a brand new idea, is it? You mentioned the Tucker 48 earlier.
Yes, the 1948 Tucker Torpedo. It had a third headlight mounted right in the center of the hood that was mechanically connected to the steering linkage.
So if you turned the wheel left, the light physically looked left.
Simple, mechanical, and brilliant. The Citroen DS did it in the late 60s with a really complex system of cables and ropes. Piano wire, essentially. But modern AFS does the exact same concept using GPS and steering angle sensors. It knows a curve is coming before you even turn the wheel, and it swivels the LED modules to illuminate into the bend.
That is cool. But the holy grail right now has to be the matrix light, the glare-free high beam. I have seen videos of this in action, and it genuinely looks like magic.
It is the biggest leap forward in decades. So imagine driving down a pitch-black road with your high beams on constantly. Maximum brightness, never dipping them.
You would be the most hated person on the highway.
Normally, yes. But with Matrix LED, a forward-facing camera scans for other cars. When it sees one, say, an oncoming semi-truck, it doesn't dip the whole headlight beam.
What does it do?
It selectively turns off individual LED pixels within the light cluster.
So it basically draws a black box around the other car?
Exactly. It creates a dynamic shadow tunnel. The other driver is sitting perfectly in the dark, totally comfortable. But everywhere else, the trees, the deer on the shoulder, the empty road ahead is still lit up with full high beam intensity.
And it tracks them.
It tracks the car as it moves, keeping it locked in that shadow block while lighting up the rest of the world around it.
That sounds absolutely incredible for nighttime safety. Why don't we see these on every car in the US? I feel like I've only seen them on European car reviews.
We are right back to regulations. The U.S. law, FMVSS 108, was written decades ago in a way that rigidly defined a quote-unquote high beam and a low beam. It didn't have any legal framework for a high beam with dynamic dark holes carved into it.
So it's just illegal by default?
Until 2022, yes. The Audi Matrix system, for example, has been legal in Europe for years. But if you bought that same car in the U.S., the automakers actually had to use software to permanently disable the Matrix feature before selling it to you.
That is so frustrating.
The U.S. finally amended the rule in 2022 to allow it, but the specific testing requirements are still slightly different from the international standard. So it is taking time for manufacturers to certify and roll them out here.
It's always the paperwork, isn't it?
Always. Innovation moves at the speed of light, but regulation moves at the speed of a committee.
So we have gone from literally burning acetylene gas tanks strapped to the running board all the way to digitally controlled pixels that can actively dodge oncoming cars. It has been a massive evolution.
It really has. And I think the major takeaway here is that lighting isn't just about seeing.
What else is it about?
It is about communication. It is a constant active negotiation between you and the other drivers out there.
Right, it's a battle between physics and physiology.
Exactly. You need to see the assured, clear distance to stop in time. But if your super bright laser light prevents the other guy from seeing his lane, you have just created a totally different hazard.
So here's my final thought for you to chew on as we wrap up. We are rapidly moving toward a world of autonomous vehicles. Cars that drive themselves.
Right.
They use LiDAR, they use radar, they use cameras that can see perfectly in infrared.
They don't need visible spectrum light to drive safely.
Exactly. So in, say, 20 years, if the car is doing all the driving, do we even need headlights anymore? Or are the lights just going to be there for the pedestrian so that we can see the car coming?
That is a fascinating question. The headlamp might transform from a critical tool for the driver into a pure warning beacon for everyone outside the car. Or maybe they just disappear entirely.
Something to think about the next time you flip that switch. Thanks for listening to this deep dive into the world of automotive headlamps.
Drive safe out there.
See you next time.